Hello. For a long time, people have accepted that everything in this world is made of atoms, and we believe the atom to be the most basic unit. So an atom is supposed to be indestructible, it's supposed to be indivisible. That's until J.J. Thomson discovered the electrons. So it looks like the atom is not a uniform sphere. It contains electrons. But electrons are negatively charged, and we know the atom as a whole is neutral in charge. So came the Thomson plum pudding model. So imagine the atom to be like the plum pudding, where electrons are sprinkled in a positively charged mass, just like pudding in a plum. Then another person called Rutherford had to come along and prove Thomson wrong. To cut the long story short, by studying how alpha particles are scattered by gold atoms, Rutherford realized that an atom must have a very dense nucleus, which is positively charged. But then if electrons are negatively charged and nucleus is positively charged, why don't the electrons all get sucked towards the nucleus? So Rutherford proposed a planetary atomic model. He imagines that electrons are all orbiting around the nucleus, similar to how satellites orbit the Earth and therefore do not have to fall back towards the Earth. But soon people realized that this model cannot be right. It turns out that charged particles undergoing acceleration must emit EM radiation continuously. So these electrons, they are undergoing centripetal acceleration continuously, and therefore they should be emitting EM radiation continuously, and therefore they should be losing energy continuously, and therefore they should collapse onto the center of the atom in a blink of an eye. So this is where Niels Bohr came in. Because he combs his hair so neatly and because he doesn't stick out his tongue, he's not as famous as Albert Einstein. Also, as his name suggests, he has a very boring personality. However, as a physicist, he was brilliant. So when looking at the problem of the planetary model, Bohr made a connection with another problem. Do you see this neon sign here? Very colorful, right? Now, most people do not know that the light of a neon sign comes directly from the light given off by hot neon gas. So hot gases emit light, and they emit very colorful light. So this is the color of helium gas, this is the color of neon gas, argon, and so on. And there's something about the light given off by hot gases. Now, if you take the light given off by a hot object, for example, a glowing tungsten filament, if you pass it through a prism and study the spectrum of the light, you see a continuous spectrum from the reddest red to the bluest blue. But if you pass the light given off by a hot gas through a prism and you study the spectrum, you will see a discrete light spectrum. You realize that hot gases emit light at only particular wavelengths, and every type of gas has its own unique discrete spectrum. And this is rather interesting, isn't it? So Bohr was thinking hard about this problem, and one night he had a strange dream. He dreamt that when he went to an ATM to withdraw money, his requests were all rejected. Only when he tried to withdraw 110, 220, 330, 660, 880 and 990 was he able to get the money out of the ATM. Very strange, right? Then Bohr realized what is the reason. Apparently, his bank account has a very strange account rules. He's only allowed to keep these amounts of money in his bank account. So let's say he currently has $9.90 in his bank account. Can he withdraw $1? No, he cannot. Because if he withdraws $1, he'll be left with $8.90, which is not an allowed amount. He also cannot withdraw $2 because $7.90 is not allowed. So what can he withdraw? He can withdraw $110, which will bring him to another allowed balance amount. He can also withdraw $330, he can withdraw $930. But there were three other withdrawal amounts that were allowed, right? That will come from if he had currently $880, then he can also make a withdrawal of $220 or $880. Or if he currently has $660, then he can withdraw $660. So when Bohr woke up, he realized what is happening in the atom. So he said the Rutherford model is wrong in the sense that these electrons shouldn't be allowed to orbit at any orbits they want. Instead, the electrons orbiting the nucleus are only allowed to orbit at certain radiuses. So for example, this is an allowed orbit, this is an allowed orbit, this is an allowed orbit, but this is not allowed, this is not allowed, this is not allowed. Now every allowed orbit has an associated energy. So this diagram here will represent the allowed energy levels in the atom. So if you have an electron currently at this energy level, then it can emit a photon by transitioning to a lower energy level. And the energy of the photon that's emitted should be equal to the difference in the energy levels. So if the electron is to make a down transition from E3 to E2, then it would emit a photon with energy E3 minus E2. There's one more possible down transition here, going from E2 to E1, which will emit a photon with energy E2 minus E1. The energy of the photon emitted, which can be written as hc over lambda, is always equals to the energy gap. Now, do you realize that this can explain why hot gases emit only light of particular wavelengths. So Bohr went on to study the discrete line spectrum of hydrogen gas. Why did he pick hydrogen? Because hydrogen is the smallest atom, just one proton and one electron. If you cannot solve hydrogen, there's no point trying helium, neon or whatever. So he took notes that the hydrogen's emission spectrum has lines at 410 nanometers, 434 nanometers, 486 and 656 nanometers. So he kind of worked backward to figure out what are the allowed energy levels in a hydrogen atom. So with that, he concluded that the allowed energy levels in a hydrogen atom is given by this formula here. So the lowest energy level turns out to be negative 13.6 electron volt. This is called the ground state. If a hydrogen atom is already in its ground state, it cannot lose any more energy. But the atom can be excited if the electron is brought to higher energy levels. So for example, let's say the electron is now sitting at n equals to 3. So when the atom loses energy, the electron can make a down transition from n equals to 3 to n equals to 2. And in the process, it must emit a photon. And we can now calculate the energy of this photon because it must correspond to the energy gap. Turns out the photon emitted must have the energy of 1.89 electron volt, which corresponds to 656 nanometer. This is great because 656 is indeed one of the emission lines of hydrogen gas. Let's try another example. Say the electron is currently sitting at n equals to 4. If it were to de-excite to n equals to 2 level, the photon emitted must have energy of 2.55 electron volts, which corresponds to 486 nanometer, which is great because 486 is the other emission line. So do you realize that if the energy levels of an atom is discrete, then its emission spectrum will also be discrete. Because when you de-excite from n equals to 4 to n equals to 2, you must lose 2.55 electron volts. You cannot lose 2.60 electron volts or 2.50 electron volts. That's why the atom can only emit light with wavelength of 486 nanometers, not 500, not 450. But then it cannot be just 4 lines, right? Because it looks like there are more than 4 possible down transitions. So indeed there are. For example, all those that de-excite to the ground state, all those that de-excite to n equals to 2, all those that de-excite to n equals to 3. But it turns out only these 4 lie in the visible spectrum. These 3 involve down transitions with smaller energy gaps. So the photons they emit pack less energy and they turn out to fall in the infrared region. On the other hand, these are rather big down transitions, which results in photons of much higher energy and much shorter wavelength, and they turn out to be ultraviolet light. So now the Bohr's model actually not just explains the visible spectrum, it also predicts that there should be more emission lines in the infrared and in the ultraviolet region. So people go back to the laboratories and look for these emission lines, and turn out the predictions of the Bohr's model is correct. And so the Bohr's model replaced the planetary model of the atom. Actually, this model also became outdated in just a few years' time. We no longer believe that electrons orbit the nucleus, but the idea that an atom has quantized energy levels, the idea that an atom can only possess specific amounts of energy is still valid even today. Alright, that's all. Ta-ta!